Hi, everyone. I'm just going to wait a little bit longer for more people to join, and then we're going to get started.
Yazi kunilungu ilindile ukuthi khanti iyangena manje uqhamuka seyakhuluma ngingatoto.
Okay, let's get started. So last time we did the fundamental theorem of calculus part 2. I just want to do a little recap on that before we move on to indefinite integrals. So that's going to be today's work. So recap on FTC 2. Okay, so the fundamental theorem of calculus part 2, that was an alternate method of finding a definite integral. So if we have the integral from a to b, f of x dx. Okay, so we have this definite integral. Remember, the first method we looked at was the limit of a Riemann sum. And it took a long time to solve those problems, okay, because you had to do the summations and the limits and all of that. However, with FTC part 2, we saw that this is a lot easier to calculate these things with, because all we do is we find any antiderivative, capital F, we evaluate it at B and subtract the same antiderivative evaluated at A. And we could use this to calculate definite integrals. So let's just make a little note that this capital F here is any antiderivative of the little f. Okay, and we said that because you could choose any antiderivative, let's choose the antiderivative where the additive constant is 0. Okay, of course, you can pick whatever you like because we proved that it works with any constant, but just in your working, you can choose that constant to be 0. Okay, it just simplifies things a bit. Okay, so that's what we covered last time. What we're going to do now is come up with a new notation, a very helpful notation for the antiderivative. So, we will use this notation, okay, as inspiration to come up with new notation for the antiderivative. Okay, so what do we do? Well, we're going to keep with the same style that we have over there. Now, for the antiderivative, remember, if I give you a function f, little f, then you can find the antiderivative, capital F, right? That's how we've been doing things. Now, we're going to come up with this new notation inspired by this notation for the definite integral. Now, this is just notation, right? But it's helpful. And we will see why now. So we're going to keep the integral, right? This integral sign, but we're not going to put the bounds, right? There's no bounds involved because, like I said, you're just taking a given function, little f, and we are producing the antiderivative. So there's no bounds, but we keep this elongated S shape. Then it's going to be f of x dx is equal to, now we just want this to be the antiderivative. So we will write capital F of x. Okay, that's it. Nothing too complicated here. And we can see the similarities between this notation and the previous notation. So for a definite integral, like we looked at last time, we have this elongated S shape. So the integral from a to b, and then that is given by the antiderivative at b minus the antiderivative at a. Okay, we covered that before. Now this new notation, very similar. We write the integral, but no bounds. Okay, no bounds because we're not evaluating any areas. We're just finding the antiderivative. So we have the integral f of x dx is equal to, and then the antiderivative as we know it from before. So that's just the antiderivative. There's nothing new here. It's just a different way of writing the antiderivative. Okay, and then a lot of times, this capital F, we also include plus C. Now, this plus C is redundant because remember, this capital F here should already have the plus C, but it's just extra emphasis that this is an antiderivative or a family of antiderivatives, should I say. So this gives us the family of antiderivatives, just like we've been working with from day one. Okay. Are there any questions about this new notation that I'm introducing? Okay, so all this funny stuff on the left-hand side here is just notation for that capital F function. Okay, but we will see as we go through, this notation is very helpful when we are solving integrals. Okay, there's some properties involved that makes it quite useful. Okay, so this thing on the left just represents the antiderivative like we've seen before. Okay, so not much new going on here. Let's look at an example where we use this new notation. Okay, so just a little example. So we want to find the integral of x squared dx. Okay, now again, this isn't a definite integral because there's no bounds. So all we're doing is finding the antiderivative. So in this case, we look at the function inside here. It's just going to be x squared. How do we find the antiderivative of x squared? Well, we add 1 to the exponent to make it 3, and then we divide. So that's going to be 1 over 3 x cubed, and don't forget the plus c. Okay, so you see it's just the antiderivative like we've been using all along. It's just a different way of writing it. Okay. So this is exactly the same if we wrote f of x is equal to x squared. And then this means that the antiderivative capital F, is 1/3 x cubed plus c. Okay, it means exactly the same thing. Okay. Are there any questions so far? Okay, I've got a question here. Can you repeat the whole thing? You had a problem with connection. Okay, so do I need to repeat? Okay, well, this beginning part, you don't need to worry about that. But basically what we're doing here is we're introducing a new notation for the antiderivative. So remember before I gave you a function little f of x, and I asked you to find capital F, finding the antiderivative. We're doing exactly the same thing here, but instead of writing capital F all the time, we write this integral symbol here. Okay, so we write this over here instead. Okay, and that is inspired by the notation that we used for the definite integral. So instead of doing the definite integral from a to b, we instead write just the integral sign. We don't put the bounds. And because we don't put the bounds, we don't evaluate the antiderivative at the bounds. We just write the antiderivative, capital F of x. And then don't forget your plus c. Okay. So whenever you're working with antiderivatives, you always put the plus c. Okay. So it's just new notation. It's nothing, it's not new work or anything like that. Okay, is that all right? Okay, awesome.
Yes,
okay,
sir.
Awesome, glad to hear it. Let's look at another example. Okay, so let's say we want to find the integral. Okay, so from now on, I'm not going to say I want to find the antiderivative, okay, because we know it's the antiderivative. I'm just going to say the integral of something. Okay, but you know, it means exactly the same thing now. So the integral of sec squared x dx is equal to, what do we get? So remember, if I say the integral of sec squared x dx, all I'm asking for is the antiderivative. It's just another way of saying the same thing. So what should I get here?
So you should get tan x plus c.
Yeah, perfect. Yep, tan x plus c. Always remember your plus c over here. Okay, good. So I'm sure everyone's following now with this idea of calling it the integral instead of the antiderivative. Okay, but it's the same thing. We're just finding the antiderivative. Okay, so now that we know that this symbol, the integral thing, is just the antiderivative, we can find properties of this notation. Okay, I'll show you what I mean now. So some properties, and these properties will, of course, help with your calculations. Okay, so firstly, if I have the integral of some constant times f of x dx, remember how we treated constants with antiderivatives? We could take constants out. So we can do the same thing here. Yeah. For example, the antiderivative of 2x squared is exactly the same as 2 times the antiderivative of x squared. Okay, you can take the constants out. They don't affect the calculation. Okay. Number 2, if I have the integral of f of x plus or minus g of x dx, this is equal to, again, remember what we did with antiderivatives. If I gave you like a polynomial and I asked you to find the antiderivative, remember you can find the antiderivative by finding the antiderivative of each term individually. So we can do the same thing here. The integral of f plus g is equal to the integral of f, and then we can have plus or minus the integral of g. Yeah, so this means that we can find the antiderivative of individual terms if we add them or subtract them. Okay, number 3, the integral dx. What do you think this will be? Okay, think back to, sorry, what was that?
X.
Yeah, perfect. X, but remember plus c. Okay. because we are still dealing with antiderivatives, you have to add the plus c. Okay, let's look at some more properties. If I have the integral of x to the n dx, okay, again, this is just an antiderivative, so we use the antiderivative power law. You add 1 to the exponent, divide by the new exponent. So we get 1 over n plus 1, x to the n plus 1, and don't forget your plus c. Okay. Next, so these are the properties, the basic properties that you should know, and we can use these to help with the problems that we have. But you see, these are exactly the same properties as antiderivatives, but we've just written them using this integral notation. Okay, so it's just a notation change. Okay, so next. Important trig integrals. Okay, so, oops, important. So with these now, it's just a list of trig integrals. I don't expect you to prove any of these, but I do expect you to memorize them. Okay, so there's not many, but they are important to know to get through the calculations quickly. So the integral of sine x dx, again, it's the same thing as just saying the antiderivative is going to be minus cos x plus c. Okay, the integral of cos x dx, that's going to be sine x plus c. Okay, then we just had this now, the integral of sec squared x dx, that's going to be tan x plus c. Okay, and then the integral of cosec squared. Okay, so remember 1 over cos gives us sec, 1 over sine gives us cosec. So those are the two reciprocal trig functions. Okay, and then this is going to be minus cotan x plus c. Okay, two more. The integral of sec x tan x dx, that's going to give us sec x plus c. And lastly, the integral of cosec x cotan x. So again, your reciprocals, that is going to be minus cosec x plus c. So let's just zoom out here so you can see all of them. There you go. Okay, so these are very important. Again, you don't need to prove them. We actually did that last time when we looked at the antiderivatives. I just expect you to memorize them so that you can quickly write down the answers if these come up. Okay, so you don't need to prove these. But please remember them. Okay, there's not many. Okay, are there any questions so far? Okay, let's look at an example now that we have some starting points here. Okay, so example number 1, we want to find the integral 10x to the 4 minus 2 sec squared x dx. Okay, we want to solve this. Now, as it is, if we consider this inside part as a function, we can't directly write down the answer. Okay, we need to do a bit of work. So what we do is we separate this into individual problems that we can solve separately. Or if you can do it all in one step, that's perfectly fine as well. So we can write this as the integral of 10x to the 4 dx. Okay, so we just use the power rule on that one, minus 2 times the integral sec squared x dx. Okay, so I'm just explicitly writing down that we can do each part separately. But if you want to do it all in one line, that's perfectly fine. You get all the marks for that. So what's this going to be? Well, the first one, we just use the power rule. We add 1 to the exponent to make it 5. Divide by 5, we're going to get 2x to the 5 minus the integral of sec squared. We just had that now. That's going to give us 10, but we've got a 2 in front. So it's going to be 2 tan x, and then don't forget your plus c. Okay, you have to have plus c over there. If you don't put your plus c, you're going to lose some marks there. Okay, are there any questions about this one? Okay, see, not too bad. Let's take a look at example 2. We want to find the integral of cos theta over sine squared theta d theta. Okay, so now I've just done a little change of variables. So instead of writing the function in terms of x and then having dx, now the function is in terms of theta and we have d theta. Okay, it's just a renaming. There's nothing different going on here. Okay, now this function inside, there's no standard antiderivative that you should know of just by looking at it. So instead, we need to do a bit of manipulation. Sorry, got a question here. Can you please make more example of a much more complicated integral? Yeah, we're getting there. Baby steps. Okay, you can't run a marathon before you walk. Okay, but I like the enthusiasm. Okay, so we have the integral of, so cos theta over sine squared theta. We can do a bit of manipulation here. So we can write this as 1 over sine theta, and then cos theta over sine theta d theta. Okay, so we just separate it out. Now, why did I do that? Well, because this first term in brackets, 1 over sine theta, that is going to be cosec theta. Okay, and then cos theta over sine theta, that's going to be the reciprocal of tan. So that is cotan theta, d theta. And we know this. We had this in our table earlier. This is going to be minus cosec theta. And don't forget your plus c. Okay, so you see that sometimes you can't write down the answer immediately. You may have to do some working out along the way. So let's just write some manipulation or algebra may be needed. Okay. Okay, and someone wanted to do a more complicated integral. So I think I'm going to have to make test 1 a bit harder then, if you think these are all the easy ones. Yeah, no problem. I can edit the test. Okay, let's have a look at something more complicated. So now we have, what example is this now? 3. Okay, a little bit more difficult. So we have the integral of 2 plus tan squared theta d theta. Okay, so now the integral of tan squared, that's not known already. That's not in our list of things that we know. So we need to do a bit more manipulation. So we can write this as 2 plus sine squared theta over cos squared theta, d theta. Okay, so we're getting somewhere. Now, this sine squared, we can rewrite as 1 minus cos squared. Okay, now why do we do that? Well, if everything is written in terms of cos, maybe we can get some simplification done. So this is going to be 2 plus 1 minus cos squared theta over cos squared theta. Okay, so we wrote everything in terms of cos. We can then separate this fraction out and simplify. So this is going to be the integral 2 plus 1 over cos squared theta minus cos squared theta over cos squared theta, d theta. Okay, and then this is going to be the integral 2 plus 1 over cos squared theta, that's sec squared theta. Hey, we know that. We know how to do that one. Minus 1 d theta. So 2 minus 1, that gives us 1. So the integral of 1 is just going to be theta. The integral of sec squared, that's going to be tan. And don't forget your plus c. Okay, so just a little note here. You will also need to know your trig identities. Okay, so for some problems, you'll have to use some of your trig identities to solve that. Okay, are there any questions on this one? Okay, I don't want to do too many difficult examples here because this is still the early stages. Later on, when we do the more complicated integrals with U substitution and trig substitution and integration by parts and all of that, then it gets much more complicated. But for now, you don't know many rules yet, so we keep it simple for now. Okay, but I will be posting some more difficult homework problems for you to try. Okay, so that's about it for this indefinite integral stuff. I just want to introduce the idea of the net change theorem. Okay, so that's the next theorem we need to know. And we're going to be looking more into that on Monday. Okay, so let's just introduce that now. So this is the net change theorem. Okay, so we've done with the indefinite integrals for now. This is something new. So recall that the integral from a to b of f of x dx is equal to the antiderivative at b minus the antiderivative at a. Okay, so we know this now. We've done that lots of times. So what I want to do now is replace f with f prime. So instead of integrating a function, we are going to integrate a derivative. So what this means is we're going to be looking at the integral from a to b. F prime of x dx is equal to, what should I have on the right-hand side now? So
just f of x.
Yeah, so it's going to be not the antiderivative capital F, it's going to be little f at b minus little f at a. Okay, so it's like I took the derivative on the function f to get f prime, and then I took the derivative of capital F and I get back little f. Okay, now the thing I want to point out is the application of this. So this goes back to your differential calculus when you looked at rates of change. Remember that the derivative means rates of change. Okay, for example, velocity is the rate of change of distance. Or if you have like a container that is has a hole in it, it loses water at a certain rate. So that would be the rate of change of volume. So you can have rates of change of distance, rates of change of volume, you can have rates of change of speed, and so on. Okay, just rates of change of things. Now, what this means is that on this other side, we have f at b minus f at a. So remember, f could be volume or distance or whatever. This gives us the net change. The net change in f. Or you can think of it as f at the final state minus the initial state. You know, like b is the upper bound and a is the lower bound. If we think of it as time, b could be the final time and a could be the initial time. So this would be final minus initial. And what do we call final minus initial? We call that the net change. Okay, so we have something like that. So a quick little example. Let's say we are measuring like a child running, doing like a race or something, and we know that the speed is equal to 4t minus 1 meters per second. That's their speed. Now, what we want to know is if that's the speed, then what is the distance that they covered? Okay, this is a rate of change problem because we know the speed, that is the left-hand side of this formula. We want to know the total distance covered, well, that's the right-hand side of this formula. So the integral from, let's say, over 0 less than or equal to t less than or equal to 5. So from 0 seconds to 5 seconds, we want to know the distance. So we integrate from 0 to 5, s of t dt. This gives us the final distance. Okay, so this is the person's position at the end of the race minus the initial distance. So this is where they were at the beginning. So final distance minus initial distance is the distance traveled. Okay, and that's the idea that we're going for. We have some function that represents the rates of change. We want to know what is the net change over some interval. So we integrate the rates of change from the initial to the final, and that gives you the net change. So I just want to leave this little quote here. Okay, so on the left-hand side, we can imagine that as the sum of small changes. So the sum of small changes. So this is just a way of remembering the integral of the rates of change gives us the total change, or in brackets, the net change. Okay, so that will help you remember this theorem. Okay, so the sum of small changes, that is the integral of the rates of change, gives us the total change or the net change. Okay, so let's actually do this calculation now with this child running and see what we get. So the distance is equal to the integral from 0 to 5 of the rates of change of distance. Well, that's just speed. So that's 4t minus 1 dt, because we're working in time. So this is going to be 2t squared minus t from 0 to 5. Okay, we're just doing a definite integral here, nothing crazy. So that's going to be 2 times 5 squared minus 5. So that's going to be 2 times 25. That's 50 minus 5. So that's going to be 45 meters. So this kid was running at this speed between t equals 0 and t equals 5. After 5 seconds, the kid ran 45 meters. Okay, this is the application of the net change theorem. Okay, so you see it's not too bad. Are there any questions about the net change theorem? Okay, so this example was just in terms of rate of change of distance, but of course, the applications go on and on. We can do the rate of change of volumes of things. We can look at how the mass changes across a solid. Lots of examples. Okay. So this we will then go over again next week. For this week, you should be able to finish tutorial 1 now. So you should have been able to do all the questions up until the last question. The last question is on indefinite integrals, which we finished now. So you should be able to finish that over the weekend, and then we will go through that on next Wednesday. Just before we go, remember next Wednesday, we have the next tutorial test. That one is going to be written, okay? It's going to be a written tutorial test, and it will cover what we've done this week. So that will be the fundamental theorem of calculus part 1 and the fundamental theorem of calculus part 2. Okay, it won't be on the net change theorem. That will be for next week. Okay, are there any questions about what we've done today? Okay, if you do have any questions later on, please just let me know. Okay, and please do the tutorial. And if you have any questions while you're doing the tutorial, I'm always available to help you out. Okay, but remember your test is coming up very shortly on the 9th of March. Okay, so not next week, the week after that. And I have posted the scope in the email. So if you have any questions about the scope or anything about the test, also let me know.